Welcome back to Math 103. This is video number 18 on measuring power. We are ready to address our last question on the topic of measuring power. Given a specific number of players, how many sequential coalitions are there, and how long does it take to list all of them? In other words, what we're really getting at here is how much work is involved in computing the Shapley-Shubik power distribution. We have already alluded to this problem in the current chapter and referred back to the previous chapter where we had the question of how many different ways are there to fill out a preference ballot with a certain number of candidates. This is implicitly the same question as we're asking now. So let's recall the thought process. There are as many sequential coalitions with two players, let's call them A and B, as there are two-letter words using A and B without repetition. So we can have the two-letter word AB or the two-letter word BA. Similarly, we can have two different sequential coalitions, AB and BA. Right? This question of listing words, what are all the ways to list words, and what are all the ways to write out sequential coalitions, these are the same question, and we'll get the same answer in terms of how many ways there are. So once we've convinced ourselves that there are two words using the letters A and B without repetition, how many three-letter words are there using A, B, and C? Well, using a reasoning process that we saw at the end of the last chapter, if we already have our words A, B, and BA with two letters, where can we put C into such a word to make a new three-letter word? Well, we can put C at the end, we can put C in the middle, or we can put C at the beginning, so we end up with two new words, plus two more new words, plus two more new words. So the total number of orderings of A, B, and C, that is to say, the total number of words or the total number of sequential coalitions using A, B, and C, well, that's 2 plus 2 plus 2 equals 6, or 3 times 2 equals 6, 3 blocks of 2. So that's why there are 6 sequential coalitions with 3 players. We can keep going with this reasoning. Once we know that 3 players give rise to exactly 6 different ways of writing them in order, we can go on to ask what is the effect of adding a 4th player, D. We get a block of 6 words from adding D at the very end of one of the words that we already had. One of the 3, we can take 3-letter words, each of them, and add D at the end, so that's a new block of 6 words. We can insert D into the 3rd position of a new 4-letter word, so we get 6 distinct 4-letter words that way. We can put D into the 2nd position and get another 6 4-letter words, or we can put D into the 1st position and get 6 more 4-letter words. Right? So that's a block of 6, a block of 6, a block of 6, another block of 6, 4 blocks of 6. So producing this systematic list of all the different 4-letter words consisting of A, B, C, and D gives us 6 plus 6 plus 6 plus 6 of them. That's 4 times 6. But wait a minute, this is looking very familiar. Okay, so this is 4 factorial different ways of producing these words in order. 4 factorial different sequential coalitions with 4 players. Each one of those 4-letter words in order corresponds to a sequential coalition. Great! We've really seen this logic play out, so we're convinced now that we can continue this approach for any number of players. If you added in a 5th player, E, to our 24 words that are already 4 letters long, then you will produce 5 blocks, 5 separate blocks of 24 letters each. So 24 words with E at the very end, 24 words with E second to last, etc. So you'll get 5 different blocks of 24 letters, a separate block for each location where E could go in a word. So 5 times the number of 4-letter words. So that's 5 factorial words. That's 120 words. So there are 120 different sequential coalitions with 5 players. Conclusion? However many players there are, call it n, there are n factorial, the number of players factorial, different sequential coalitions. Okay, great. So that was a very nice little mathematical exercise. What does this have to do with your life? this is much more of a practical question in the current chapter about measuring power than it was in the previous chapter about all the different ways to fill out a preference ballot. Because when you apply the Shapley-Shubik power distribution method, when you compute that Shapley-Shubik power distribution, you really do have to do all this work and list all the sequential coalitions. Alright, so if there are 10 players, there are 10 factorial sequential coalitions to list. That's over 3 million. Okay, so your computer can still handle that. But with 20 players, there are now in the quintillions when you go and compute it. Right, this is a huge number, and by the time you're computing 50 factorial, your calculator might display the output in this way as 3.04 e plus 64. What that means is 3.04 times 10 to the 64. This number is incomprehensibly vast. Right? So to get our minds around why that's important and how vast it is, let's ask the following completely practical question. If you needed to compute the Shapley-Shubik power distribution for a system with 50 players, okay, that's actually slightly smaller than the full U.S. Electoral College, which has 51 because of D.C. If you needed to do that, how long would it take? So let's first look at how long it would take on a computer which lists 1 coalition per second, and then we'll think about faster computers after that. So try and answer this question before going on. How long would it take to list 50 factorial sequential coalitions on a computer which lists 1 coalition per second? How many years would that take? The first thing to note is that it will take 50 factorial seconds to list all 50 factorial coalitions at a rate of 1 per second. Right? That's why we're doing 1 per second, to make this nice connection so that we'll see how to make life more complicated afterwards. Okay, so for now, you're working on a slow computer that can only do 1 per second. You have this much work to do, 50 factorial items to list, so it'll take exactly that same number of seconds on your slow computer. All right, so how do we convert 50 factorial seconds to years? Well, if we take 50 factorial seconds and divide by the number of seconds in a year, then we'll convert from seconds to years. Okay? So number of seconds divided by seconds per year tells us the number of years. So how many seconds are there in a year? Well, there are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year if you forget about leap years. So multiplying those all out together tells you the number of seconds in a year. Okay? So 50 factorial divided by this number is still a very large number. Okay? So converting from seconds to years still left us with a vast number of years on the order of 10 to the 56. How vast is 10 to the 56? Well, the universe is only 13.5 billion years old, approximately, and 13.5 is 1.35 times 10 to the 10th. Not even remotely in the same ballpark as 10 to the 56th. Okay? So there is no chance that your computer is actually going to be able to compute your answer for you in a practical amount of time. Okay? Suppose we go to a faster computer. How long would it take to list those same 50 factorial sequential coalitions on a computer which lists 1 million coalitions per second instead of 1 per second? Okay. So go ahead and try to answer that question before you continue. Now we've already done the hard work of figuring out how long this computation takes on the slow computer. The fast computer we're discussing is exactly 1 million times faster. Right? So that will make the computation time only 1/millionth of what it had been on the slow computer. Okay, that's useful information. That means we just have to take the amount of time from the slow computer and divide by 1 million, and this is what we obtain. Now you could ask your calculator to compute this, or you could note that 1 million equals 10 to the 6th, and that's helpful because 10 to the 56 divided by 10 to the 6 equals 10 to the 50. right? You keep the base and subtract the exponents. All right, so that tells you, without a whole lot of extra computation, how long your computer will need to work, even if it's the faster computer, and it's still an utterly impractically vast amount of time. It cannot realistically be done. So what does this have to do with your life? And this is important. There are practical problems which are so computationally intensive that it is impractical to solve them. We like to think you just give it to the computer to do, and the computer just does it. But that's not a practical option in many cases. This example involved a perfectly straightforward practical problem. You want to know how power is actually distributed in the full U.S. Electoral College, and it turns out that that computation just can't be done. The fact that there's such a thing as a practical problem that is impractical to solve because it is too computationally intensive, the fact that that exists, you need to know that. As an educated citizen, you need to know that such problems do exist.